just a test to see if my webcam gets recorded too. Okay, so I'm not sure if my webcam is actually showing up while I'm recording. My attendees view doesn't have like a little inset that shows my webcam. So part of the feedback I'm going to ask you for right now is whether or not that is showing up when I use GoToMeeting to record my sessions here. So I'm going to go ahead and solve tonight the first problem that your daughter sent me, Nicole. Sorry, Petey. The first problem says a bow is fired horizontally from a wall 52 meters high. The arrow's speed is 115 meters per second. Part A, how far away from the base of the wall does the arrow hit the ground? Part B, what's the final velocity of the arrow? And part C, what's the flight time of the arrow? I already have the problem uploaded from a PDF file. I typed it out in a Word document and saved it. So I already have that uploaded in the whiteboard. I can see that that's too small for someone in the audience to actually be able to read it easily. But this is just a trial run to see how this all works. So the first place we're going to want to start, and I am still getting used to both this whiteboard tool and to my new tablet writing device. The first place we're always going to want to start is with a picture. That might seem, yes, I want my pen tool, thank you. That might seem silly and self-explanatory, but it really does help, and it doesn't have to be to scale, but it really does help us anchor the problem in a physical reality of if we saw this happening, what does it look like? So y'all get to witness my amazing stick figure art. So we have bow and arrow like this. Okay, fantastic. So we're saying that the arrow is going to be launched from 52 meters high. And the arrow is going to follow some sort of parabolic trajectory through the air and land somewhere out here, a distance I'm going to call delta x away from the base of the wall. So we're going to assign that 52 meters the variable delta y for change in vertical position. And in fact, in a minute, we're going to go ahead and assign that a negative value because the arrow is ending up 52 meters below where it started. So one thing we might want to include in our picture is the place that we're going to call the origin, the 0 position for the x direction and the 0 position for the y direction, with a little set of axes like that to indicate which way is positive for x and which way is positive for y. And in fact, I don't know if it's worth it to, yeah, we'll go ahead and undo. We'll put plus y like that and plus x like that. Oh yes, and I forgot one important thing, which is also helpful to label. There we go, trying to get that pen tool to work, is that the arrow is going to have an initial x velocity because it's launched, it's fired horizontally. It's going to have an initial x velocity of 115 meters per second, like so. So the next step, after we have sketched a diagram that includes the starting point for whatever's going to happen, we need to indicate the ending point for whatever's going to happen, and then we need to label whatever physical variables we can that are given or asked for in the problem. So the next thing I want to introduce is one of my favorite tools for solving any kind of motion problem. I learned this from a textbook where we can make a table to fill out, and the table lists all of our kinematic motion variables in one dimension, and then I'll show you my twist on it to make it work for 2 dimensions. I'm going to go ahead and change colors because I can. So in our table, we're going to list across horizontally. We know we need t for time. Delta x is the change in horizontal position. V naught x is the initial horizontal velocity. Vx will be the final horizontal velocity. And then ax is the horizontal acceleration. We can actually go ahead and start filling that in before I show you the twist on how to make this work for 2 dimensions. So we know part A asked how far away from the base of the wall does it hit the ground. So I'm going to put, actually, I'm going to make that red because that's more fun. Oh no, we'll make it pink because pink is an option. So we're going to do a big old question mark in a fun color, and I'm going to put an A beside it because it's for part A. So we're going to find that in this problem. We're given that the arrow is launched horizontally at 115 meters per second. So that's V naught x. We'll fill that into our horizontal table. And now the key for projectile problems is to remember that if it's a projectile, then the only force we're going to deal with is gravity, downward, that's vertical. So we should already know that in the absence of air resistance, there is no horizontal acceleration. If you've already studied forces, then you know it's because there's no net horizontal force in the horizontal direction. And that means that Vx is still going to be 115 meters per second. So we know that there's constant velocity in the horizontal direction. And then acceleration, uniform acceleration, in fact, in the vertical direction. So here's my fun little trick to make the table work for 2 dimensions. We're going to come do the same thing. We're going to keep t in the corner because t is shared. Something cannot take more time to travel vertically than it does horizontally. Doesn't matter what's happening. There's one time, so we put time in the corner. And then we're going to list our vertical motion variables, delta y, v naught y, vy. So those are the initial vertical velocity and final vertical velocity, and ay, the vertical acceleration. So what I like about doing this is it really helps us make visual the fact that the variables that apply for the horizontal direction, we're going to write in the table horizontally. And then any variable that applies to the vertical motion, we're going to put vertically in the table. I mentioned a while ago, we're going to say the vertical change in position is negative because the arrow started 52 meters higher than it ended. So its final vertical position is 0 and its initial was 52. And we always know that a change is final minus initial. So 0 minus 52 gives us negative 52 meters. It dropped 52 meters. Since the arrow's fired horizontally, V naught y is going to be 0. Vy, we don't need to worry about that yet. We're not given any information. We're not asked about it. So we're going to put an X in that box. And then we know that we're dealing with the acceleration due to gravity for the vertical direction. So this table is my favorite way to have students organize their information for projectile problems like this, or any two-dimensional motion problem. So we notice something here, that we don't have a value to plug into the box for time. And when I look across, I see 3 numbers that are useful because they're all different for the vertical direction, and then I don't know t. And here's the thing, guys. Because we have constant velocity horizontally, really, we kind of don't even have to worry about Vx and Ax. We kind of don't really need them, at least not right now. So I'm just going to X those out for this example. So we really only need delta x, v naught x, and t. Oh, well, I don't know 2 of those, and I do know 1. There is no way to have 1 equation with 2 unknowns and get an answer. So that's a good indication that we're going to have to look at the vertical information and pick an equation that will work for the vertical direction to get time, even though time was part C. We have to get time first, and then we can get the horizontal distance traveled, or horizontal displacement in this case. So I'm going to go ahead, because I have fun colors, I'm going to put a nice fun colored question mark in the box for time, because we have to find that first. So let's take a look down. We've got t, delta y, v naught y, and ay. So we're going to go find an equation that has all 4 of those. I'll leave it in the yellow because I can. So that'll be good feedback for me, please. If the yellow doesn't show up well, let me know. So delta y equals v naught yt plus 1/2 ay t squared. That's the only equation we have that doesn't involve vy and involves the 4 variables that we have. So now we can plug in values. All right, so we know that 0 times t is 0. Don't have to do anything with that. 1/2 of negative 9.8 is negative 4.9. So negative 52 meters for the displacement equals negative 4.9 t squared. We can divide both sides by -1. I'm not going to show that, but we end up with 52.0 equals 4.9 t squared. I'm going to go ahead and rearrange. I like to keep, even though your algebra teachers might insist that since the t is on the right, well, the t squared is on the right, it has to stay on the right. No, it doesn't. I'm going to go ahead and rewrite this as t squared equals 52.0 divided by 4.9. I was hoping to get rid of that green box there at the bottom because it's annoying, but it doesn't look like it's going to go anywhere. So I went ahead and just plugged into my calculator the square root of 52 divided by 4.9, and I got a time of 3.26 seconds. So even though that was part C, turns out we had to do that one first. So now that we have the time, we can go back to the horizontal direction, and we can pull out an equation for constant velocity, which is really just delta x equals v naught x times t. So let me grab a new color for that. And again, if you want to be precise, you could go ahead and put in the plus 1/2 ax t squared, and then we'll just substitute 0 for the horizontal acceleration, and it reduces to this equation anyway. I like to be efficient with my writing, so I'm not going to write all that extra stuff. So delta x equals 115, the horizontal initial velocity, multiplied by this time that we just found. And since the numbers given in the problem were 3 significant figures, I'm going to keep 3 significant figures throughout. So the 374.9 meters that I got here will become 375 meters. So there is my answer to part A. So to recap, so far, we draw the picture so that we can identify what variables that are given match up with the physical variables of motion that we've worked with before. And then we use this fun table that I created on the whiteboard to match up those numbers visually with anything that's for horizontal motion goes in the horizontal direction on the table. Anything for vertical motion goes in the vertical direction on the table. And then it's just a matter of matching up what variables do I have or could solve for with the equations that fit that combination of numbers that I have and things I want to solve for. So this last question, part B, what's the final velocity of the arrow? I just realized I forgot to actually find the kind of like the angle below the ground. Maybe your teacher didn't mean that. If he or she did, let me know, and I can help you with that too. So let's pick a new fun color. Let's go purple. So for this part B, the important thing is that when the arrow lands, sorry, trying to navigate my whiteboard right now. I kind of exceeded the ground a little bit in my picture. It's going to have there we go. I'm going to be clever. I'm going to have a purple arrow, and I'm going to do a red component and a blue component. So it's going to have a Vx, a horizontal component of its final velocity, and it's going to have a vertical component of its final velocity. Well, we know Vx. Vx is going to be the same as v naught x because there was no horizontal acceleration. So we're going to have to find Vy. So now we can come back and look at our table again, and really we can pick any equation that involves Vy, the final velocity. I think the easiest one is going to be, changing back to my color here, Vy equals v naught y plus ayt. So final velocity equals initial velocity plus acceleration times time. So we know that the arrow was not moving vertically at the start. We know it had an acceleration of 9.8 meters per second squared downward, thanks to gravity. We know that it was in the air for 3.26 seconds. So we get a Vy, looking at my notebook. Oh, there we go. of negative 31.948 meters per second. So I tend not to round anything until I get to the end of the problem. So I'm going to go ahead and keep all of those extra decimal places and then round to 3 significant figures when I get to the end. So now we have Vx, now we have Vy, and we can remember, I should have labeled this to begin with, and now we can remember for part B that the magnitude of any vector squared is equal to the sum of its components squared. So I prefer to write this way. I'll go ahead and do V equals the square root of Vx squared plus Vy squared, like so. And then I will substitute in the 115 squared and that negative 31.948 squared. And I get a magnitude of that velocity to be, there it is, 119 meters per second. So I could move my whiteboard around and solve for that angle for you too. In fact, let me do that. So I give myself a little bit more space, and I will draw a little sketch here for you. So if, here we go. There we go. Turn off the drag tool, I hope. There we go. Pen. Okay. So at the point of impact, the arrow is going to come into the ground like this. Well, I'm just going to make that easy and put my vector that represents the velocity of the arrow with its tail at the origin, just because that makes it easier to visualize. There we go. Where's the angle I'm going to talk about? Maybe we want to talk about the angle of the arrow's velocity being below the horizontal. So there are the components we were just dealing with. So now we can notice that the vertical component is opposite the angle. The horizontal component is adjacent to the angle. So we can use tangent. There we go. So the tangent of the angle is going to be opposite over adjacent. So, oops, I take that back. It's not 115. My Vy will use the magnitude here and not worry about the direction, because we can't have a negative value inside tangent when we're dealing with, well, I guess we could have a negative value there, but it's going to give us then a negative value for the angle, which in some ways makes sense, but I find it far easier not to put signs, S-I-G-N-S, when I'm dealing with trigonometry, and instead to just use magnitudes and then decide for myself, okay, this is an angle below the horizontal, or, you know, whatever, north of west, whatever direction you need to make it. So we'll take the inverse tangent of both sides, and then I'll go hit up my calculator to do this really quickly. because I neglected to do this part earlier. Oh, actually, I need to put my calculator back into degree mode to do that as well. Okay, so I got 15.5258, which we will, with 3 significant figures, call it 15.5 degrees below the horizontal, and I'm going to run out of space for that. So our final answer for part B would properly include both the magnitude. Oh, that was interesting. So that was a fun thing that just happened with my tablet there. There we go. And it seems like I can't actually draw any lower than I've already moved on my whiteboard. So this is, the projectile problems can be a lot of work because there are a lot of things that can be asked. But once you have a method in place for organizing your given information so that you can select the appropriate equation, it makes it a lot easier. You're pretty much always going to do one of two things. You're either going to use the horizontal direction to find time and then use time to do something with the vertical direction. Or in problems like this, use the vertical direction to find time and then do something with the time to figure out something for the horizontal direction, like how far did it go or what was its initial velocity. There might be problems where you're given time and you have to first figure out how far the thing was launched from or thrown from, but problems like we just worked tend to be the most popular. So please do give me some feedback and let me know if this was helpful, and also please let me know feedback on how well the webcam worked, if the webcam was showing up, and how well you could actually read and see and keep up with what I was doing on the whiteboard. Thank you. And